And I would like to introduce the first speaker, Olaf Pfeiffer. So Olaf studied technical computer science at the Corporate University in Karlsruhe, and he's one of the founders of the Embedded Systems Academy. Together with his partners, he wrote the books Embedded Networking with CAN and CANopen and Implementing Scalable CAN Security with CANcrypt. He is a regular speaker at the international CAN conferences and other events. Olaf is chairman of the CAN and Automation 447 standardization group that defines how CANopen is used in special purpose vehicles, including police cars or taxis, and for automotive accessories. So the topic he's presenting is a simplified classic CANopen-to-CANopen FD migration path using smart bridges. Please, Olaf, go ahead.
Thank you very much. Yeah, we came up with this actually quite early when CANopen FD was specified, because as we all know, one of the early things that was decided is that we don't have to make it backward compatible. And as we cannot run regular classic CANopen nodes with CANopen FD frames, they can not operate on the same network. And one of the logical first solutions to such an idea and scenarios, well, could it be possible to use a smart bridge that on one side talks CANopen and on the other one talks CANopen FD to provide such a bridge in a way that both the CANopen nodes as well as the CANopen FD nodes do not really realize that they are not that they are talking through a bridge. And it's not possible all the way down, but there's quite a bit you can do with it. And so the original challenges, of course, we had is the frame incompatibility, so that we cannot run the same CAN FD frame on a pure classical CAN network. And also one of the challenges with bridges is always the configuration. Now here we also wanted to see if we can get away with a smart bridge that just by listening to the traffic can configure itself, so that we do not really need to start a lengthy configuration process for such a bridge. Of course, there are some existing specification when it comes to bridges. Here they are just, some of them are listed just for reference. As I said, we really try to, in this system, try to implement it in a way that both the CANopen classical side and the CANopen FD side of the communication are not aware of the bridge at all. So, of course, we have to make a few compromises. And one of the compromises we have to make something like this work is that we define the entire network to be a single virtual CANopen or CANopen FD network. So we still stick to the limit of 127 nodes and 127 unique node IDs. So by introducing a bridge, we do not allow that the same node ID exists twice on the system. Otherwise, immediately it gets much more complicated. So possible scenario setup could be that we have a classical CANopen segment with nodes 2, 7, 11, and 12, and that we have somewhere a CANopen FD segment with additional nodes. But again, we make sure that none of the node IDs are duplicated. So within the system, all node IDs are still unique. Yeah, in this case, we can now introduce a smart bridge that communicates to one side as a classical CANopen node and to the other side as a CANopen FD node. However, we still need to have a node ID also here for the smart bridge. So here in this case, we've chosen 9, and I'll show you a little later in some of the exchange protocols how that actually works. The nice thing is, as I said, by just listening to the traffic to the network, there's quite a bit that a smart bridge can learn. Of course, once we fire the system up and assuming the bridge is one of the first devices to start, or it is ensured that at some point there is a NMT reset so that everybody restarts, then of course we immediately know on which side of the bridge is our NMT master. Is that on the classical side or on the FD side, depending on from which side we get this message. And by listening to the boot up and potentially heartbeat matches, we also get the location of each node on the system. So if we go back to the previous slide, the bridge, by listening to the messages and boot ups, will pretty quickly get a picture of which nodes it has connected on which side of its port. Of course, once we introduce an active scan and allow the smart bridge to also actively use USDO and other protocols, then we can learn much more. But that's really, yeah, depending on how far you want to take this concept that I'll show you soon here. Now, with the additional, this minimal information we have, we'll introduce that the bridge does unconditional forwarding for the following messages. Unconditional means that really every NMT master message, for example, that we see is passed on from one side to the other to ensure that everybody sees this. We do the same for all the boot up and heartbeat messages to ensure that also all the other nodes know where each system is and or that it's available in the entire system. Then for PDOs, we'll do conditional forwarding. And here, of course, a half automatic version only really works for PDOs with data links of smaller or same as 8. And there are some protocols, specifically the emergency, the SDOs and USDOs and larger PDOs that require translations. So here the bridge needs to do something and to the messages to make them compatible for the other side. Let's start with the emergency. That is relatively simple because the classical CANopen emergency has a length of 8 bytes. There's a 16-bit error code, and there's an 8-bit error register, 5-byte manufacturer info. If we compare that to the CANopen FD emergency message, then we can actually see, oh, the same existing classical CANopen emergency message is still part of the new longer messages. There are just some additional fields. So when forwarding this message from one side to the other, then the bridge would need, from the classical side to the FD side, expand and add these fields. Those that it doesn't have the information available will just have to go, unfortunately, then with defaults. But things like timestamps is possible. The bridge could have a timestamp, so that could be handled. And vice versa, if CANopen FD emergency is seen on one side, it could easily be forwarded to the classical side by just extracting the original portion here of the emergency. So here on the FD side, it's a total of 20 bytes, and lost on forwarding, then unfortunately our logical device number, CIA specification number, and the timestamp, unless it's used by the bridge. So nothing essential, well, not perfect. Whenever you lose something, it's not perfect, however, doable. Much more challenging is the USDO and SDO translation, because really, as I said, our goal here is that the nodes do not need to know that they talk to a bridged node that even is of a different type, meaning it's implementing classical CANopen while I am a CANopen FD node and vice versa. So the communication translation needs to be in that way fully transparent, and the awareness does not need to be at any of the participating nodes. Again, as with the emergency, there will be some things as a compromise that we'll have to get rid of and that we lose. For instance, in USDOs, we have also type information available, while SDOs do not offer type information, so such information will simply not be available on the classical CANopen side. Let's have a look at what the segments are when we do SDO to USDO forwarding. Let's assume we have on the classical CANopen segment some sort of manager with the SDO client, and there is somewhere here on the CANopen FD segment is a node number 6, and somewhere in between here we have our bridge. So what happens is that the manager already knew from forwarding by the smart bridge the heartbeats or boot ups that the node number 6 exists somewhere on his segment. That's what the manager believes. So the manager can send out an SDO request to node number 6. Now, the smart bridge already learned that node number 6 is here on this side, so it can translate this into a USDO request. And for CANopen FD, where USDO requests always have a source and a destination, it will forward it to node number 6 and use its own number, node number 9, as the response, so to say, so that node number 6 can reply to node number 9. So for node number 6, it will look like the request came from node number 9. Then on the way back, the node 6 will simply produce its regular USDO response. So the node number 6 doesn't know that in the end this came from a different segment. And again, the bridge sees the response, can extract the relevant information, and here on the classical CANopen side, reply with the SDO client response. So here to the manager, it really looks like node number 6 was available on the network because it sends a transmit and it receives the response, request and response. Now, if we look at the other way around, from a USDO to SDO forwarding, then let's assume here in this example that we have a request from node number 5 to node number 11, because this number, this node number 5 here also learned during boot up that there was somewhere a boot up from node number 11. So it will send the request from 5 to 11. And of course, the smart bridge needs to monitor all USDO communication. So it knows, oh, this node here, node number 5, tries to connect with number 11, which is on my end. So again, it can interfere or take this message and convert this into an SDO client request here on this side. Of course, that requires that actually we are allowed to use the SDO clients here on this side. So we translate it to an SDO client request on this side. Node 11 doesn't know really where a USDO client request comes from anyway in classical CANopen. We don't know that. We just reply to it. And so it simply produces the response. And here on the response on the FD side, the smart bridge just has to pay attention that it's not using its own node ID, but it's using again the node ID 11 as the source going back, so that node number 5 is not suspicious as to where the response came from. So this works fine and easily if we can do it with expedited transfers on both sides, meaning that the maximum data size we transfer also on the FD side is not bigger than 4 bytes. Now, if we use more than 4 bytes, it gets a little bit complicated, but manageable. We have implemented a prototype to show that. And here the smart bridge actually needs to do some buffering. So let's look at the timeline. What happens when we transfer more than 4 bytes? So we get from the CANopen FD side an expedited USDO request that could have more than 4 bytes to be written to a destination. Then on the classical side, this is translated into multiple segmented transfers going back and forth. And only with the last response will the smart bridge send the response back to the initiating node with the response. As you can see here, the entire system, of course, requires that we have a reasonable timeout, because the USD timeout here of a typical node would probably be much faster, because if I just send an CANopen FD expedited request, I get an expedited response, typically relatively fast. So one of the things that the CANopen nodes on the FD side really need to understand and participate in is that their timeouts are configured long enough. The bridge itself, I'll give you a little bit of performance later on one slide, but that is really fast. So it really depends here on both nodes, how long the segmented transfer takes. If there is a timeout involved here, also a delay of multiple of tens of milliseconds, then of course an entire setup like this gets challenging, but there are quite a few systems where this actually works. There's unfortunately something we cannot catch with the Smart Bridge if we are doing it the other way around. Now, if we are writing a segmented transfer from the classical side to a single expedited USDO on the FD side, and let's assume now the response coming back requires segmentation, then we can only start the segmentation after this response came back. So here we send one read, one upload request, get the expense, and now we get the segmentation. And oh, sorry, what I'm hinting at, what makes it more challenging is not this scenario, but the write scenario, because here the timeouts and segment timeout still works fine. We have, of course, a little bit of a delay here between those two, because there's a forwarding on the right side. But the thing I wanted to point out already is the segmented write. So here we do on the classical side a segmented write. The segmented write started, but the Smart Bridge cannot really initiate a communication on the FD side until it has all the data. And so only once all the data is here, it can do the expedited USDO transfer and send the response, which means that if this entire transfer is something, for instance, to an object dictionary entry that does not exist, well, unfortunately, we will not get the USDO abort here at the beginning. We will only get the USDO abort, the SDO abort for something like this here at the end. So this is something that does not fit 100% into the classic CANopen conformance, specifically the abort code for object does not exist. However, the classical CANopen node would still see that in the end the transfer failed. There was just a bit of unnecessary communication in between already. This could have been earlier. Well, of course, the Smart Bridge can start learning which objects are available in which node, but I think that is then the lists and tables get a little bit too long on that end. So again, here, the downside is any sort of abort coming from the server here will only be recognized on the last segment. As I said, we did a sample implementation of this, a prototype implementation to do some testing, and I wanted to show a little bit of the performance. We've taken an off-the-shelf existing hardware here, in this case from Peak, one of the Pecan router, and they use an LPC 4000 microcontroller running at 120 megahertz. And with that, we are with processing delays, and these are processing delays in the bridge, are really going down to single microseconds. So within just a few microseconds, the message will be passed on from one side to the other. That's the nice thing today with, if I compare how long many of us here have been in the business, but today the microcontrollers are so fast and efficient that such delays and processing time really go down, especially when there's nothing else to do for this microcontroller. I mean, routing here between two CAN ports is literally the only thing that the processor does besides maintaining the lists, what is where on the system. Of course, there's always a delay because each message is fully received before the forwarding and the processing starts. So any message we have to fully receive, then we start the processing, and then within a few single microseconds, the forwarding starts. So what have we achieved to here, and which challenges remain? Well, for PDOs longer than 8 bytes, I don't see any automated way to handle those, so they really require some manual reconfiguration. So that is not something the bridge can do easily automatically. Also, there's then with PDOs longer than 8 bytes, there's the transmission trigger challenge, meaning well, if the data comes from multiple PDOs into one, what do we take as change of state? Do we wait until all the bits and bytes of a PDO are available? So there's quite a few challenges here. Also, we haven't done any segmented USDO support. So right now, the maximum size is 54 bytes, a single USDO expedited transfer. However, segmented should just work fine if needed. We need to increase the buffers and timeouts again. However, we are not really keen on implementing this until somebody truly sees a need for it. And the other remaining challenges is regarding the routing. So really for instance, with PDOs, the question is, do we need to decide for each PDO if this needs to be routed at all, or if there are multiple bridges involved, which way do they take? There's no self-learning there in this case too. And of course, we haven't really tried to do anything here with the sync, because once you use PDOs and sync combination, where a lot depends on synchronization, there's always a delay introduced. So any application using that would need to do a careful evaluation if it's feasible. And also another one remaining challenge is the multiple USDO to one SDO. Right now, if the bridge receives multiple USDO client requests coming from the USDO side to going to the same destination node ID, it causes the USDO abort busy. So this is as if the node currently has only one server implemented and that server is busy. So this is not so unusual in these systems. When it comes to the CANopen manager and master, then of course there are some limits in scanning and learning options for the bridge. So here one option could be to also implement an SDO manager on the classical side on the bridge to better manage the SDO channels on the classical side. A little outlook for the options to do multiple segments. So in theory, the logic within the smart bridges is really port independent. So it could be any number of ports connected. And as long as there are no rings or loops, the algorithm currently used works just fine. So we could have any combination of classical CANopen and CANopen FD segments in one network. So honestly, as I said, there are some compromises and drawbacks, but this could be a solution for all those applications who quickly want to introduce and mix a few off-the-shelf existing, for instance, classic CANopen devices with a CANopen FD implementation, so that not all of the devices in one system immediately have to do the step to going to FD. So if the number of nodes and the functionality is within limits and nobody is trying to run here aiming for the 90–100% close performance of bus load and performance, then this could be a solution. With that, I conclude my part of this presentation, and I am available for questions and answers later.